predicted true, and so you can put it everywhere, all right? And then at the beginning of the collection, you have a mark table that's going to tell you what's dead and live, and it's either auxiliary data or embedded in the object header. So one of the tricks is to reverse the meaning on each other collection if all your metadata is in the object header. But if your metadata is separate from your objects, you can just clear out all the metadata to zeros, and then ones mean the object's live. Okay, and then you have a mapping from the metadata to the object store. All right. Then you say, what are the roots pointing into the heap? So you go scan the stacks and scan the global variables, and then once you're finished with that, then you start performing the transitive closure. When you're finished with the transitive closure, you sweep the blocks, and then you resume the mutators. Okay. So this is called a phase-based approach. Until work packets, everybody just use this. All right, so work packets observe. One of the things that we observe here is you can start your transitive closure once you have even one root, right? You don't have to wait to go through all the roots to start your transitive closure. You do have to wait until your mark table is reset, though that's a hard constraint. So there's more areas to get parallelism out of, and I'll show you a bit more in a minute. So in practice, this is measured GC phases. Here we have resetting the mark table in the prepare block and you can do that in parallel, so you get a lot of parallelism. Those are different threads resetting the mark table, but you have to wait for all of them to finish, and then you can start scanning the roots, and you can see that one of the scan classes takes a lot longer than the others, and so there's a lot of empty time there, and then we start tracing. Okay. So scan, roots, and tracing give you a lot of opportunity to get rid of that dead space if you start tracing as soon as you've got even one root. So that's the opportunity here at the lower levels. Is that a question or just an itch? All right. Okay. So poor load balancing, not very good parallelism here. And if we look at the original OpenJDK implementation, which also uses phases as well as the original version of all the MMTK phases, you've got two problems, right? And so this is the phase problem, and I already talked about the monolithic problem. Okay. So the key idea is each work item is the smallest unit of work, and it's about like here's a unit of work that scans part of the stack and says looks for the pointers. So or a heap. This is an object that we need to trace to find to mark the liveness. Or I already said that one. And then, so the smallest unit of work is something that you have to do, like scan an object, look at a root, clear the mark table, and divide it up into some unit of work on dividing up the metadata, so you can do that in parallel. And so work item stealing is a great approach that's been used for decades, and the work stealing work by Charles Lyserson and Bobby Blumoff was really great abstraction that tons of people have used, and this work builds on that work stealing abstraction. So you can steal, so if you're a thread and you've run out of work to do, you can go steal a work item from another thread. So that maximizes parallelism. So the kernels are these small functions that process a list of the same type work items. So you have a kernel that says, here's an object to scan, and this is the way you scan it. So each work item also has code that's associated with it to do the work for its item. All right? So here's an object that you need to scan, and here's the kernel that scans it. So you take objects as an input for each object in your list. You attempt to mark the object if it's not marked already, and if it is marked, if you mark it, then you start scanning the object. And so what do you do when you scan the object? You look at all the pointers in the object and you enqueue them for or you enqueue the target of, you can do it either way. You can enqueue the pointers or you can enqueue the target of the pointers, and that has some trade-offs that I'm not going to go into today. Okay? All right. So then these small functions that operate on objects now and process the same work items are highly concentrated. That has so many advantages. Now I only have to prove that that's correct. I only have to debug that part of the code. It's not spread all over 200 and different methods and 30,000 lines of code. All right? And so they're also the hottest loops in the GC. So then performance optimizing is also benefited because you only have to focus on performance optimizing each of these kernels rather than profiling and finding where in your code something's hot or stuck or not scalable. So better locality, highly generic, code reuse. All right, I already talked about that. All right, now let's go back to our phase design and add parallelism with the work packet design. All right, so now we stop the mutators. We can start scanning the roots. But we can't perform the transitive closure until all the mutators are stopped and all the we've reset the mark table. But as we scan the roots and generate work for transitive closure, we just have to wait for some of that work to appear, and then the transitive closure starts going once the two dependencies are satisfied. Ricardo?
Do you think that thinking about parallelization inherently makes you make things more modular and independent of each other and reusable?
Not for everybody. But it should, because reasoning about parallel systems is hard, right? And so the more you add abstractions that make it easier for you to reason about, like the work packet abstraction, like work stealing, then the more likely you are to get that system highly performant, correct, and not and be able to fix it when things go wrong. In the back.
Yeah, my name is Tyler. So based on your last description, should I think that there's like a dotted line from scan roots to transitive closure in that graph?
That's right. It's generating work for the transitive closure, but it doesn't require that phase to finish, right? So this graph doesn't quite show that there is still, like you're getting, there's a data dependence even if there's not a control dependence, right? This is only showing the control dependencies. All right. And then the abstraction called work buckets says put work in the other person's queue, all right, essentially, and then operate on it at some granularity is the scheduler of what's in the work buckets. So I'm going to talk very briefly about the scheduler. All right, so and when you prepared the reveal slides, which I like a little bit, but not completely. Okay, so you have to describe the data dependencies, and you have to put things in the work bucket for each of the phases. All right. So marking requires a properly initialized mark table, so you can accumulate work for the transitive closure while you're waiting for all the mutators to stop and and the mark table to be completely reset. So then a work bucket is a set of packets with the same dependencies, and so as soon as those control dependencies are satisfied, then you can start operating on them. And then we have what's called dependency-based scheduling, and that's agnostic of the GC worker threads, but the workers pull packets out of these buckets to execute, and then you update the bucket status when there's no more work to do, and none of the predecessors can produce work. They're completely finished and they can no longer produce any work, like the scan routes is finished, so it can't produce any more work. So that work bucket is closed and won't have any more work to do. So that's how it basically works.
Yes. So does the scheduler take into account temporal locality? Like, for example, like if I just scanned a route, it'd be nice if while it's still in cache, I do transitive closure on that route.
Not really. But that's important, right? When you do the work. And when you, like if you just enqueue the pointer and not the target of the pointer, you're not accessing that object twice, right? Enqueue the address instead of visiting the object. And then when you visit the object, do all the scanning of the object and the marking of it so that you're not visiting it twice. Good question. Ricardo, did you have something else?
Sort of, but it's a little, I'll just ask it. So when you're having the workers do these two different jobs,
Right.
How do you architect that so that the workers aren't just this like disjunctive mess of like, if this tag is set, I do this thing, and this like,
So each worker has a set, like, so just like work stealing, you need to worry about granularity, right? So if you have too few, if you're just doing one work item at a time and then rechecking the work buckets, that's too expensive. But then if you take too many, then other worker threads sit idle. So we actually have a 2-level scheduler to make those determinations. But since I was supposedly doing this whole talk in an hour, I know I didn't cover those details, but those are in the paper and should be available soon. Okay. So now I'm going to move to the evaluation of work packets. So for the code reuse part, most components are reusable. So we have 10 GCs implemented in MMTK right now, and the algorithm agnostic scheduler is used across all of them. The common work packets are 28 of the work packets are reused across all 10 GCs, and then there are 49 GCs. And in fact, LXR is our biggest unique work packet designed because we didn't have a base reference counting collector implemented in MMTK. It was in the previous version of the toolkit, and we hadn't really implemented, or you would have, if we'd had a base reference counting collector, we would have reused at least a few more of these packets. All right, so what are the common work packet designs? Route scanning, marking and evacuation, mark table sweeping, stopping and resuming mutation. So things you would expect that you should be able to share across all these collectors. All right. So each GC needs to declare its work packets and any dependencies these work packets have on the data dependencies and the control dependencies. So then you can, the other thing that this lets you do is if you just want to analyze route scanning, it's easy to put the performance monitoring or the correctness monitoring or whatever's going on at the time, either correctness or performance are the two things that are always going on. So you can monitor just the method that you think is screwing up, right, on whatever. So 10 GCs in MMTK take up 45K lines of code, which is less than some of the monolithic implementations and on the order, but only a few lines more than a lot of the collectors. And there's the LXR specific parts of the design are 3.8K lines of code, even though because it's the most unique one. And then IMIX is 0.5K lines of unique code. So that, we found that really astonishing when we measured it. All right, and not only that, you get nice performance wins. So we implement the same framework with phases and without phases, but not apples to apples with a completely different implementation like we had in the more traditional versions of the world in older. And so we see a time for stop the world. GC time is going down by 7 points, and total time and stop the world time for LXR for IMIX as the base system, and then for LXR it's going down by 6%. So that's a pretty astonishing good performance improvement over the phase-based approach. We were surprised at that too. All right, lessons for parallel programming. There's still new abstractions to invent, and I welcome you all to go out and invent some more. And there are other systems that could benefit from describing their data and control dependencies a little differently, and also the operations that you need to do on that data in a kernel, and then blobbing those around to be scheduled. So we think this is a generalizable abstraction. And then the two-level scheduling, which I didn't talk about, also works well. All right, so this was 25 years of garbage collection innovation, learning from abstraction from innovation, and then deeply understanding the performance, memory, cost trade-offs so that you could innovate, and creating a virtuous cycle of abstraction and innovation. So the abstractions helped us innovate faster, and then we we could do this additional abstraction and get rid of these penalties that we're seeing in parallel computation. So building a virtuous cycle. So many of you are at the beginning of your career, and you think how can you have strung together 25 years working on one topic? I don't know. but you have that opportunity. And I really love this space as a deep and foundational enabling technology for all of programming languages that require garbage collection. I've also worked on C and C++ memory management. And the reason that I find this space so fascinating is because it underpins the connection between the programming language and the hardware. And hardware is changing. And programming languages are changing, and applications are changing, and they need to be glued together. All right, so now, with my last 20 minutes, I'm going to talk, well, let me take a few more questions. I'll take 5 minutes of questions, and then I'm going to do a different topic. Aaron?
Yes, so in the, about 3 slides ago, when you talked about the packet model,
Yeah?
on top of my mind, this is really just for stop the world garbage collectors, right?
This works for the LXR has concurrency, and so it's also doing some of this concurrently. Work packet, LXR uses work packets for its concurrent work as well as for its stop the world work. The main benefits were on breaking the phases, but it helped with concurrent tracing too. Right, because you could do that better.
Right, I'm just wondering, if you have a fully concurrent garbage collector, how would you even model it? Because it kind of requires the reason that what's saved and what's not.
So you still have to scan objects, right? And you still have to have integrity of that the pointer pointing to the object hasn't been, it is still. So what you don't want is to lose an object because the pointer was mutated, and your snapshot at the beginning is that this object should still be treated as live. So the pointers into that object, that code still has to be proven correct concurrently. It might not help you with, like, I wasn't involved in the proofs of this model, so I can't tell you how they handled the concurrent, and I didn't read the paper either, because it's no longer my day job to work on memory management. So that, I think that in the proof paper, you get the answer to that question. Good question. Sorry, I don't have the full answer. When Ricardo or Dustin, because you guys love to ask questions.
I wanted to know if you could connect incremental garbage collection with yesterday's topic of abstractions and whether or not the things that you've done within the study now would fall in the category of incremental garbage collection.
So the implementation, so the evaluation, actually, let's get, this is, the IX is just the base IMIX, stop the world IMIX, and LXR, the bottom graph, is a concurrent collector and incremental with reference counting. And so these algorithms are in both. They benefit mostly the pause time, like getting that pause time down, because that's where phases are slowing you down. But the model is used for all the phases of the collector. Like, so if you go back to the red, blue, orange parts of the collector, they're all in there, right? That's how they're implemented for the bottom. The bottom is just measuring the pause time, because that's easier to measure.
And is incremental garbage collection typically involved in only reference counting? Or is
Well,
there-
it's the most immediate. It can do things most incrementally. And you can just stop the program a lot more often and collect, and that's more incremental, but then it has higher costs, because that stopping the program is expensive. Ricardo, and then in the back, Ty next.
This is about engineering abstraction. So I find that I don't know that I need an abstraction until I need it, and it's too late. Or I'm doing some abstraction that turns my class into a thing doer, and it's now impossible to reason about because I'm making no assumptions. So I'm wondering, sort of like two parts of the question: what do you think makes people make monolithic things? Like, is it time pressure or something else? And the other thing is, like, how do you hit the sweet spot with abstraction, or is it just experience?
So my view is that there's a virtuous cycle between making things the smallest possible unit that you can think about and abstraction. And that there's emotional and benefits as well, because if you get the smallest possible thing working and it works, you get to feel good, right? And you, like, if I got something working today, even if it was something small, or I just wrote a bunch of code and I have no idea that it works, like, those are very different ends to your day, okay? And so if you can break things down into smallest possible units for you, and then keep going, and you have to come back sometimes, and that smallest unit didn't do quite all the things you needed it to do, and make and iterate that way, then you're more likely to come up with the abstractions earlier rather than later. And if you sit down and write up and say, oh, I'm just going to write like a huge amount of code, and it will not benefit you in the long run for emotional reasons and for technical reasons, right? So that this is a way of thinking about problem solving, actually, that will help you problem solve better and build abstractions. So that's my advice. And then once you've written something monolithic, it is very hard to back out of it. I agree with that. Ty?
Yeah, I was wondering, it looks like MMTK has some integrations with existing programming language runtimes. Wondering, like, is that a part of the MMTK project, and have any of these languages decided to use it as their like default allocator?
So Shopify is one of the biggest contributors to Ruby, and they are deeply dissatisfied with the Ruby garbage collector. And so they started partnering with Steve on using MMTK for Ruby. And so the first part of that use of MMTK for Ruby is published in ISMM last week, right? So that, and I don't know how Steve and the Shopify Ruby folks got connected, but now both Jishwen and when you have job offers from Shopify, I don't know if they'll end up there or not, but so I think that they have very strong, they see the performance potential and they would really like to have it. So that's basically how these things happen. Some important user of that programming language implementation becomes dissatisfied, looks for something better. And that happens very, very slowly, right? The fact that G1 is still the default collector in many JVMs is a testament to how slowly people want to change their base underlying infrastructure without expertise in-house or shared vision, right? But that's, we're still using Linux, right? Because people are afraid of change, and people have invented much better languages and systems for OS, but no one's changed yet. Although I think there's opportunity with LLMs to translate into old languages into new languages, so maybe things will go faster in your future, or you could make them go faster also. Okay, I want to talk a little bit in my last 15 minutes, and we'll see. This is the second talk I wanted to give, and this is me personally, not Google or anybody else, talking about why research culture matters and what research mindset is. And I'm not sure how much of research mindset I'll get to, because I will end at 10:20. But, and why I think it leads to more innovation. And this isn't like some generic statement I'm making. This is you, if you create a good research culture for yourself and for your colleagues, and even when other people are not participating in a good research culture, that you will personally be more innovative, okay? So this isn't like generically the community will be more innovative. This is you, if you think about things in an open-minded way, if you collaborate well, if you build up the people around you, if you don't make assumptions about people because they look a certain way, and you try to work with everybody, you personally can collaborate better, and when you're collaborating better, you will produce better research. Okay, so we have some myths in the computing culture versus what the truth is. So there is a very widely held myth that we have some founding fathers of Silicon Valley and everything emanated from them. So no, all these people had strong partnerships and teams, okay? And hundreds of thousands now at my company. My company had 3 people. They had 2 new entrepreneurs who had NSF fellowships, like many of you working at Stanford. And then they had one more, Eric Schmidt, one more senior guy who'd worked at companies before, and the 3 of them managed to build my company, right? As the leaders of that company. So even if you say, oh, the leadership is concentrated in one person, that's not true either. And that wasn't true for Bill Gates' company either. There was Paul Allen, and I drive by the Paul Allen AI Center every day on the way to Google. It's right next door. All right. Similarly, at Facebook, we had Sheryl Sandberg making a huge difference there. And at Apple, we had Steve Wozniak really getting Apple started. And if you move forward, then we had Joni working with, he was the UI person working with Steve. So even if you look at the very top of the leadership, these people weren't working alone. And then in order to do anything real, they had to collaborate. So what does that say about teams, okay? You have to work in teams. So if you measure, this is a small study done in a controlled environment, but I think it has some interesting results in it. But of course, small studies done in controlled environments don't generalize perfectly to your real world. So they have 190 ad hoc groups of about 2 to 5 people. And then they had measurements of the solutions, the interactions of those teams. They judged the solutions of the teams. They judged the interactions. So they recorded them and then scored them. And then they had IQ and gender and et cetera. And then what do you think the #1 predictor of performance of the team was? Someone new, you two have been great. Right. Size, no. In the back? Interactions, that's right. Average social sensitivity of the group. What does that mean? They listen to each other, okay? When the other person talked, they didn't interrupt. If they didn't understand what that person was saying, they said, I don't understand what you're saying. Could you try again? All right? Equality of conversational turn-taking. You've been in meetings, I have a set of meetings I go to right now where one guy sucks all the air out of the room. So it's my fault, I guess, as a leader at Google, I should prevent that instead of just being sad about that. And you can't, and those are the kinds of talks I give myself, actually. That it is my job now to make sure that the teams I'm working with have equality of conversational turn-taking, and that we're hearing from people who don't naturally speak up. There was somebody saying, after 6 hours of lecture and hallway talk and the meals, that he has to go just lay down. You're an introvert. Somebody in the room needs to make sure you're talking, right? Because you're not naturally, or if you are that introvert and you're not naturally speaking up, please speak up more. And write down what you want to say, but don't interrupt. All right, and then number of women in the group, of which I found very, I don't know if I believe this, because I have lots of very socially sensitive, turn-taking men that I work with, but it was higher correlated with women. Ricardo?
This might be too specific, but how do you encourage introverts to speak up without feeling like you're blasting them, like putting them on the spot?
Just say something gentle like, do you have anything to add? Right?